Swayam Prabha. Digital India. Educated India.
Welcome back to the discussion sessions of manufacturing automation course. Let me remind you, in our last sessions we have discussed different types of part orienting devices, and we said that for small engineering parts particularly, this is very crucial that all the parts have to be transferred to the automatic assembly machine with the right orientation. So, therefore, different kind of devices are used, so that the parts which are coming with a wrong orientation, they can be reoriented. So, we discussed that there are active devices and passive devices, orienting devices, and they may be also classified as the in bowl type and the out of bowl type. Now, in bowl tooling, those are the orienting devices which are normally used inside the vibratory bowl feeder or any other feeders, and out of bowl systems or out of bowl toolings as we call, those are normally used in the feed track, and that is the outside the vibratory bowl feeder. So, therefore, those orienting devices which cannot reorient, which reorient by rejecting, let us say. So, they cannot be used outside the bowl or as out of bowl tooling, because out of bowl tooling cannot reject the parts to the bottom of the bowl, whereas those orienting devices which are used inside the bowl, they can be either passive or active. Active orienting devices, they reorient the parts, whereas the passive orienting devices, since they are inside the bowl, so they can actually reject the parts if the parts are coming in a wrong orientation, and those parts will go back to the bowl of the feeder and they will again get recirculated. However, it is not very desired that the parts are rejected, because in that case, as we discussed, that not only the bowl, but the parts get worn out. This discussion was followed by the feed tracks, and we said that the feed tracks are used to connect the bowl feeder with the assembly machine, because the bowl feeders, they cannot be placed very close to the assembly machines, and therefore, there should be a track for the parts to go to the assembly machine. In the feed tracks, we said that there are vertical delivery feed tracks and there are horizontal delivery feed tracks. Now, in case of the vertical delivery feed tracks, we have the parts coming down the feed track from the bowl feeder by means of gravity, and that is why we said that the TP, that the time taken for parts to go down the part track, that depends on the gravity. Now, in the case of horizontal delivery feed track, we have actually analyzed, and we found out that this finally the AN by GN, which is the normal track acceleration, that depends on few factors like the ratio of the length and the radius of the curved portion, if you remember, the dynamic coefficient of friction, and so on. So, these discussions we had in our last sessions. Then we said that the problem becomes that when the feed track is filled up, then the parts actually can jam in the exit of the bowl feeder or inside the track, or even at the entry of the assembly machine. Now, the reason behind this is that normally we keep the conveying velocity of the bowl feeder little more than the parts required in the assembly machine, in the sense that from the outlet of the bowl feeder, the parts coming out will be little more than the parts that can be taken by the assembly machine. and this is simply because we ensure that the assembly machines do not starve. Whenever they need a part, they can get it. Now, in that case, if the feed track becomes filled up, then the parts cannot actually go to the assembly machine and they cannot be stacked inside the feed track, and then they can clog the exit of the ball feeder. So, then we discussed that we have to ensure that this does not happen. We have to solve the problem caused by overfeeding, and consequently is the problem of where a simple control system can be employed that incorporates sensing devices located at two positions on the feed track. So, what we said earlier actually is this, that so when the automatic feeding devices are used on assembly machines, the mean feed rate is usually set higher than the assembly rate, as I said. This is to ensure a continuous supply of parts at the workhead. Under these circumstances, the feed tracks become full and parts back up to the feeder. For vibratory ball feeders, however, this method is not always satisfactory. With these feeders, the parts in the line in the feed track are usually prevented by a pressure brake. If you remember, we have discussed the pressure brake, which limits the path, and it makes the path less so that the parts cannot negotiate this from interfering with the orienting devices mounted on the ball feeder track. If a part filters past the orienting devices and arrives at the pressure brake when the delivery chute is full, it is rejected back into the ball. If this occurs too frequently, as I discussed, excessive wear to both the ball and the parts can result. So, to prevent this, there is a method that has been adopted in the industry to solve the problem caused by overfeeding, and consequently is the problem of where a simple control system can be employed that incorporates sensing devices located at two positions on the feed track. Let us look into this diagram, and here is a line diagram showing that this is a ball feeder through which the parts are coming and coming to the feed track. This is the feed track, and this feed track brings the parts to the workhead for assembly. Let us say these are the assembly workheads. Now, so that the parts are sufficient in the feed track and the feed track does not get filled up quickly, or it cannot be kept vacant, there are two sensors. One is in this position, this is called the on sensor, and another sensor is kept, it is an off sensor, meaning that when from the ball feeder the parts will be coming to the workhead, and suppose the workhead is working and the parts will not, next part will has to wait for to go to the workhead, and these parts can be stacked up to this position. As soon as the part level goes beyond this, there is an off sensor and it will put off the feed track. That means, from the ball feeder the parts will not be able to come to the feed track, and then from here when the sensor keeps the feed track off, then the parts will go as the workhead will keep taking the parts for assemblies, and as soon as the part level goes beyond this point. So, again this is on sensor, and this sensor will again start the feed track, so that the parts could again fill up the feed track. So, this on sensor and the off sensor, this actually maintains the problem of excessive wear of the ball and the feeder, because in this case the parts do not have to be rejected by the pressure brake, as we have discussed earlier. So, here of course, there is a depending on the types of the parts, depending on the workhead, assembly workhead, and depending on the ball feeder, the position of the on sensor and off sensor can be decided, and accordingly they are placed. let us talk about the feed tracks, different types of feed tracks. Most commonly used feed tracks are the vibratory tracks and the air assisted tracks. So, the vibratory tracks, they work in a very similar way as the vibratory ball feeder. Let us see the line diagram here. Here we have the part on the we have the track. On the track the parts are moving. Now, the track has a base here which is connected to, which is given a vibration from the electromagnet, which is mounted at the base of the vibratory track. Now, the track and the base, they are connected to each other with the springs, and those springs are similar to the suspension springs that we have seen in the vibratory ball feeder. So, that the electromagnet, when it imparts the vibration, there will be two types of vibration, one is the linear, vertical linear, and one is the torsional vibration. So, because of the combination of these two, the parts will be moving in on the track, and it will be hop and then move forward, as in case of the vibratory ball feeder. Operates at the same principles as the vibratory ball feeder. Now, it is found that the mean conveying velocity, that is F into Vm, for a wide range of coefficient of friction between the part and the track, which is mu, will be given by Vm particularly will be 4500 divided by the frequency millimeter per second. Well, this has been experimentally derived, and experimentally it has been found out that for a vibration angle of 20 degree and the normal track acceleration of 1.2, this is the case, meaning that if we have, for example, f, which is the frequency of vibration, if that is the 50 for example. So, the Vm, the number of parts or the conveying velocity will be 4500 divided by 50. So, you understand this is 90 millimeter per second. Now, this, if this is the vibratory feed track which is driven by the electromagnet, that is the vibration. There are also air assisted tracks, and the air assisted tracks line diagram is here. These are often gravity feed tracks. So, gravity feed tracks we have seen earlier, but in case of gravity feed track as well, although we are using the gravity for feeding the parts, it may so happen that the parts in between inside the feed track may be clogged. So, to assist the part to move smoothly, we have in the gravity feed track, we have the passage for passing the high pressure air, and because of that high pressure air, the parts, if they are even clogged or if the coefficient of friction becomes more while moving through the feed track, this can be eliminated. So, this is a simple diagram. This is called the air assisted track, where we have the passage through which the pressurized air is passed from a compressor, and it will assist the parts to move along the feed track. Some important points of all types of feed tracks are the following. For good space utilization, a feed track should not be too long. Now, what does it mean? That we said these ball feeders or feeders cannot be kept very close to the assembly machine. So, now if we have a feed track, now we are occupying some of the space between the feeder and the assembly machine. So, that the space could not be occupied very long, therefore, the feed track should not be the length of the feed track should be limited, and it is not necessary for the feed track to be unnecessarily long as well. Next point is the feed tracks, besides acting as a transfer device, provides a buffer stock of parts which, if a blockage occurs, will allow the work head to continue operating for a limited period. Now, initially we said that it should not be too long, but it should be sufficiently long so that the parts can be stacked as a buffer stock. Suppose if something happens to the ball feeder stops, so still the machine, assembly machine, can get the parts which are stacked inside the feed track. So, the feed track can work as a buffer stock, well, for certain time, of course. Third point is that in the event of a blockage, the parts are readily accessible. I have shown in the line diagram in the beginning that the parts have to be accessed easily. So, therefore, normally it is either open or you can easily remove the lead, so that you could access the parts. For this reason, feed tracks should be designed to allow easy access to all parts of the track. Well, either by keeping it open from some side, or it so that you could easily remove the lead. Now, our next topic of discussion is the escapements. What are the escapements? Let us see. From the feed track, the parts are coming, and there is nothing there to regulate that the parts will come one by one. Okay. But whereas in the machine, what the machine needs is the parts to come one by one. So, therefore, the escapements are the devices which provide the parts to be fed to the assembly machine one after another, or one by one. Now, escapements are activated by the work carrier and parts in these diagrams shown here. See, for example, here this is the work carrier. Work carrier will take the works or the parts which are coming through the feed track from the bowl feeder. Now, if we have a rocker arm escapement, all right, or a spring blade escapement as shown in this diagram. These diagrams are self explanatory in the sense that rocker arm escapement or the spring blade escapement, they are assisting the parts to come to the work carrier one by one. Okay. All of them will not be coming. So, when one part is coming here, the rocker arm escapement will stop the other parts from flowing here down the feed track. Similarly, for spring blade escapement will resist the other parts to come to the work carrier when one part is taken. Now, here in both these cases what is happening is that escapements are activated by the work carriers and the parts. All right. Let us see here. Here these are the two line diagrams. These line diagrams are given for the feed track here, and this is the rotary indexing table, and feed track is connected directly to the rotary indexing table. Simplest type of escapement where parts are pulled from the feed track by the work carrier. All right. So, these are the feed tracks, and the parts will be pulled by the work carriers which are located here on the indexing table. Let us say, for example, in this case this is the vertical delivery. So, this is the work carrier, okay, and the parts are here stacked in the feed track. So, as the work carrier as it is moving along the line, the work carrier will actually pull the parts one by one. So, these are the natural kind of escapements. Now, these are the simplest type of escapements, and in both the cases the what is happening is that escapements, they are being activated by the parts and the work carrier. But actual escapements are those which will activate the parts to come to the work carrier, not other way around, not that the escapements are activated, but the escapements will activate the parts to come to the work carrier whenever it is required. Let us see some of those examples. For example, this is the gate, this is called the gate escapement. In the gate escapement, this is often used for removing the faulty parts from the main flow. Now, let us say that here there is a passage through which the parts will be coming, and here there is a device. When the part is coming in this way, it will go, since this passage is open. So, this is bifurcated as you can see, and this is pivoted here. So, when the part will be coming through this, this is the rigid star which is fixed here. This will be moving from this position to this position as it is shown here in the dotted position. That means, the other passage will be opened now. Then when the part will go through the other passage, the star here, the leg here, it will actually move this to the other position. So, it will keep on moving like that as the parts are coming in one passage or to the other passage. All right. Now, this is the main use of this is to provide an alternative path for parts, in the sense that let us say at the output of this and this passage, there are two, these are going to the two different assembly machines, and two parts are needed, maybe the similar parts. So, one will be, once one will be fed from here, other parts will come after that, followed by this. Now, here this design can be actually also used by controlling this with a device or with a sensor. For example, suppose we want the faulty parts to take out. Okay. So, whenever there is a faulty part, in that case the sensor will sense the signal that there is a faulty part here, and suppose we want the faulty part to come to a particular side. So, sensor and the device will make this star in such a way, position of the star in such a way, so that this passage is kept open for the faulty parts to go, and all the correct parts will come to the other side by moving after the faulty parts have gone through this passage. The star will come back and block this passage, and it will come to this passage. So, it has different uses. First of all, once again the two parts can be fed to the two different assembly machines, or the faulty parts from the main flow can be taken out. Let us see the other escapements, types of escapements that we have. Here there is a design which is called the pawl escapement or ratchet escapement. Here there is a pawl here which is pivoted here, and which can actually oscillate like this according to the arrow which is shown here. It can go like this, or it can go back to the initial position. And here from the feed track, the parts are, these are the headed parts, they are going through the coming through the feed track, and they are hanging in the slot as we have shown earlier, that how it can be done. Now, this pawl, because of this pawl, the parts can be fed one by one, as you can see. This is quite clear from the diagram itself, that when it goes like this, it will prevent the other parts to come through the feed track, but the part which was here, this will go to the assembly machine. Then when it will go to the other position, it will actually take another part, and it will one by one. So, as the pawl is swinging, or it is reciprocating from one position to another position, then one by one the parts will be coming. Now, however, we can have the arrangement with the same kind of pawl, but the pawl design could be different. Okay. Here is the pivot. So, around this point, the pawl can actually reciprocate to and fro, and here the pawl distance from one leg to another leg is such that at a time 3 or 4 parts can be transmitted to the workhead. So, if it is required that more than one part is required for the assembly, in that case such kind of pawl or ratchet escapement can be used. So, that here finally here it is one by one, here it is more than one, and depending on the number of parts you can have the distance accordingly designed. Look at this design, for example. This is operated by linear motion. These are the parts which are coming from the feeder, and it is going to the assembly machine. Now, here there is a lever, and that lever, as you can see, if it is pulled to the right, then this lever will go in and this lever will go to the left side. So, in that case what happens, that when this is released and this is going like this, in that case one part will be released from here and other parts will be held by this pawl or by this mechanism. So, therefore, what we mean is that you have to actually pull the handle to and fro, so that parts will be coming from the feeder one by one. All right. Now, this is one handle. This can also be used like this, the same principle, that is the two jaws will be moving to and fro. So, one jaw, when this jaw is moving in, these parts in the feeder they are held and one part is released, and when this is coming in and this is going out, in that case all the parts will be stacked on this, and then this will again go in to hold this part, and this part will be released. So, the figures of ratchet escapement may be operated together or independently by cams, solenoids or pneumatic cylinders giving a linear motion, either to these two or one of them. So, I hope this is clear because the diagrams are self explanatory and the rest of the things we will discuss in the next session. Thank you very much.